Hello everyone. In the previous video we have discussed how to calculate the magnetic field at a point. It can be any point due to a cylinder which is solid, that is, which is filled in from inside. The point can be outside the cylinder, at the surface of the cylinder, and inside the cylinder also. Now in this video we are going to consider a cylinder again, but this time the cylinder is hollow from inside. We are going to find the magnetic field at all the points, that is, at a point outside also, at a point inside also, and at the surface also. So let us see how it is done. Again we are considering a conductor, but it is hollow from inside. Nothing is there inside the hollow cylinder, and we are going to consider 2 points, one outside and another inside the cylinder. We are again taking the top view, that is, if we see this cylinder from the top view is, the figure is drawn on the right, you can see here the top view. We will be considering 2 points. One point will be inside. You can see here, this is the actual circumference of the cylinder, hollow cylinder. This is the cross-sectional area because we are seeing it from the top. Now we are going to consider 2 points, one outside and another inside. And accordingly the Amperian loops which we will be drawing here will be in the form of circle. Whenever we consider Amperian loop, the radius of the Amperian loop is given by small r. So here you can see when the point is outside, then the radius, this is the radius of the Amperian loop, which is given by small r, which is greater than the capital R, which is the radius of the actual cylinder. And when we consider a point inside the cylinder, then the Amperian loop, you can see this is the Amperian loop, for which the radius again is given by small r. Okay, so we are going to find the magnetic field in both the cases. So let us see how it can be done. See here, when the point, first condition which we are considering is the point which is inside the cylinder. Now this is the cylinder, and we are going to consider a point inside the cylinder. So the Amperian loop will also be inside. You can see here, this is the Amperian loop which is inside the cylinder. The cylinder has a radius of capital R, and the Amperian loop has a radius of small r, which is less than capital R. So the condition that we are taking is small r is less than capital R. So what we are going to do is we are going to calculate the value of magnetic field at a point inside by using Ampere Circuital Law, which is integration B dot dl over a closed surface is equal to mu naught into the total current threading the loop. This time when we have considered the Amperian loop, since there is hollow portion inside the cylinder, so at this portion only air is present, no current threads through this loop. So the total current threading the loop is 0 here, so mu naught into 0. Now if we have a magnetic field here, B and dl will have the same direction, so B integration dl, B dl cos 0 is 1, so B comes out, integration dl is 2 pi r. But what you know, in the right hand side which we are getting is 0 only, mu naught into 0, which is 0. So finally the value of magnetic field is also 0, because 0 upon 2 pi r is 0. That means if the point is inside the cylinder, if it is a hollow cylinder, then the magnetic field inside the cylinder will be 0. So I hope this is very clear to you. Now the second condition that we are going to take is a point outside the cylinder, that is, the radius of the Amperian loop will be greater than capital R. So let us see that condition also when the point is outside the cylinder. Now when the point is outside the cylinder, you can see here the point which we are going to consider here is, suppose This is the point outside the cylinder which is having a radius small r, the Amperian loop. So this is the Amperian loop which has a radius of small r. Now what we are going to do is we are going to calculate the value of magnetic field there. So let us see how it can be done. The value of small r, that is the radius of the Amperian loop, which is also the distance of the point from the center, is greater than capital R, which is the actual radius of the cylinder. So integration B dot dl is equal to mu naught into the total current threading the loop. Now this time the current I is flowing through the conductor, and that I here, the top view is taken, so the current is in the outward direction and all of the current passes through the Amperian loop now. So the total current threading the loop here is given by I. So B integration dl, as we have earlier also considered the same thing. So B dl cos 0 degrees. So B comes out, integration dl is 2 pi r, which is equal to mu naught into I. So finally the value of B will be given by mu naught I by 2 pi r. This is the same value which we have derived for the magnetic field at a point due to a straight infinitely long current carrying conductor. And this value is coming to be same whether the conductor, that is the cylindrical conductor, whether it is solid or hollow. In both the cases the magnetic field which is outside the cylinder will be given by mu naught by 2 pi I by r, where we see that the value of magnetic field B is inversely proportional to the distance r. So we can draw a graph now between the magnetic field and the distance from the center. So from this point, which is the center of the cylinder, hollow cylinder, from this as we move outside the value of r increases. So here the value of small r is taken along the x-axis, and along y-axis it is the magnetic field. Now we know when the small r, that is the point if it is inside the cylinder, the value of magnetic, since it is hollow from inside, value of magnetic field is 0. So at this we don't have any curve, but when the value of r is the radius of the cylinder, that is the hollow cylinder, then we have a particular value which is given by mu naught I by 2 pi capital R. And this value from this particular point where the distance is equal to the radius of the cylinder, as we move outside, as we move away from the cylinder, the value of B decreases exponentially. So this is the exponential curve for the magnetic field, which is inversely proportional to the distance. I hope this is very clear to you. Any doubt, you can post me the doubt. Thank you.